if we have, z equals to r e to the it, how's that go? Well, we've got the modulus of, I'll do the h part first. H of r e to the it is what? 2e to the rit. 2e, no, my bad. 2e to the rit. Which is, let's write that out. That's 2e to the r cos t plus ri sine t. Which is equal to 2e to the r cosine of t, I think. See, because the other piece, this piece here, e to the I times r sine t, right? Modulus of that is just 1. That's an actual imaginary exponential. But on the other hand, what's the modulus of f of z here? So that's the modulus of r e to the it plus 3, right? Which is less than or equal to 3 plus r.
Did you mean to switch it around for h and f? Because I thought 2 to the e to 2e to the z is, oh, never mind.
Yeah, I did, but I flipped the, yeah. So, all right, so cosine t, what's the deal with t here? T ranges from pi over 2 to 3 pi over 2, right? Anyway, think about that. So cosine ranges between plus and minus 1 anyway, right? I think here it ranges from 0 to minus 1, right? So 0 is minus 1 is less than or equal to cosine t is less than or equal to 0, given the range that we're looking at. I mean, that should make sense, right? We're covering, it's the real part. It's negative. It ranges from 0 to minus 1. So how about this? If I want to make this as big as possible, what's the biggest this can be given these inputs? Two. Yeah, I think 2 is it, because otherwise we got e to the minus r, which is going to be smaller than since r is positive, right? So I think you're right. I think this would be less than or equal to 2. Now here I got to be careful. So I need the modulus of h of z, right, to be less than so I think the previous notice I have a greater than here. That was important. So this less than, actually, this is unhelpful. Okay? It's not helpful. It's not the right direction. See, because we need to put something between h and f, right? And so to do that, I need to find something smaller than f, not something larger than f. Right? So let's not do this. This is the mistake I always make when I'm working these out. So let's not do that. It wasn't wrong. It's just not helpful. So we want to see that's greater than or equal to something, right? Greater than or equal to something. So here's the deal. Absolute value of the modulus of r e to the it minus the modulus of 3. This is the triangle inequality that we use for the denominator sometimes. And that is straight up equal to r minus 3 for r greater than 3, right? So we'd have that this, so this is less than or equal to 2, right? And I'd like to say that that is strictly less than r minus 3, which then is less than or equal to the modulus of f of z for the z in the circle, right? So what do I need to assume about r to make this happen? We can add assumptions to r, right? We can start r at whatever we like. We're going to let it go to infinity. Greater than 5, right? So we should assume r is greater than 5. And of course, if we're assuming r is greater than 5, can we take the limit as r goes to infinity? Is that a reasonable assumption to maintain in the limit r goes to infinity? I think so, right? So therefore, we've got Rouche's the terms and condition for Rouche's theorem applying for the vertical and the circle. Consequently, Rouche's theorem applies, and we have shown that there's just one 0 for that equation in the left half plane. Okay. Do you understand why it was important that the inequality goes this way here? I hope I made that clear. Right, because this one is this one. Because I turned it around. So there's another example. One more example for today. Suppose we have an arbitrary polynomial of order n. All right? So example 4. Consider p of z equal an z to the n plus an minus 1 z to the n minus 1 plus dot 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 plus a1z plus a naught, where a sub n is not equal to 0. You guys with me? So let me make the following suggestion. Let's call all of this h of z. Let's call this f of z. So if we consider modulus of z equals to r, then the number of zeros for f is clearly equal to n. But notice that the modulus of h of z, right, is less than or equal to the modulus of a sub n minus 1 z to the n minus 1 plus dot 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 plus the modulus of a1z plus modulus of a naught, which we can simplify to r to the n minus 1 modulus of a sub n minus 1 plus dot 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 plus r times the modulus of a1 plus the modulus of a naught. Right. I argue that it is clear that this can be made less than the modulus of an times r to the n, which is, by the way, equal to the modulus of f of z. For r sufficiently large. let me try to bully you into believing me. So this is power n minus 1, right? So if we're at 1,000, if we're at r equals to, 1,000, then we've got 1,000 to the n minus 1 power, right? But over here, we've got 1,000 to the n, which is 1,000 times bigger. Well, what if r was 1,000,000? This would be 1,000,000 times bigger than this term. And it just gets worse the bigger r we get to. So even if this happened to be astronomical, the coefficient, right, the modulus of the coefficient in comparison to the modulus of the leading coefficient, even so, we can compensate for that by taking yet a larger r. Because this always has one more factor of r in it, which can dwarf anything that happens over here ultimately. This could be made precise, but I won't. So what does this mean? By Rouche's theorem, P of z has n zeros within modulus of z equals to r. What's that? That's the fundamental theorem of algebra. This is the easiest proof of the fundamental theorem of algebra that I know. Eh? This might also be your homework problem. I don't know.
It's close to it.
Pretty close to it, yeah. Yeah. There are more fussy estimates that can be made about the sum of the coefficients and these. If you look in the notes, there's something I skipped over that's really fussy about all that with regard to the integrals of rational functions. But anyway, so that's pretty much where we end this semester material-wise. That's it. I mean, you still got quiz to do and test to take and stuff, but I don't think there's any other material past this. Is there? Did I forget something?
This is it?
I mean, I'm gonna talk about some stuff after break.
That's
you know.
Is the stuff after break going to be on the final? That was the bonus.
Well, of course, yeah.
Okay, so.
I mean, maybe.
I know that.
I don't know.
That was the bonus.
I haven't decided what I'm gonna do after break yet. I'll think about it.
Okay.
But yeah. I mean, in the past, I've gone past this. I've covered stuff like what's that thing called? Weierstrass products or theorem or something. What is that stupid thing called? I can't even remember. See, I can't even teach. I can't even know the name of it. But there is more past here. It's just I don't get paid enough. So I'm gonna stop here.